Welcome back to another exciting day of computer vision. So we have just a couple more logistics things to talk about. Hold on, let me change this back so I can see what's going on. So we have homework 1 is out right now. You guys should hopefully be working on it. It is due Thursday. Hopefully it's not too complicated or complex. I know some of you guys, it's your first time sort of working in C. I don't think there's a ton of like crazy alloc or free and stuff or any weird memory management to do. So it's just like, hopefully you can just kind of translate the ideas in your head straight into the code and it won't be too complex. Office hours have changed for Nancy this week. She's going to be 4 to 5 on Wednesday in CSE 7 just for this week. Question? The homework is posted on the website. Yeah.
But where on the website? Because there's like homework. The homework.
Huh. Sorry. Let me get my mouse over to my side of the screen. Here we go. So in my you're going to cs.washington.edu 455. My version of the website looks like this. So it's posted once here and posted once here.
Okay.
I'll just get rid of this. Any other questions? Yeah. Yes. Yeah? Your question? Oh, okay. Cool. All right, so last time in computer vision, we talked a lot about human vision. Hold on. Gotta make sure my little clicker works. There we go. We talked about how human vision, or just vision sort of in animals, is really important. So simple eyes evolved in 23 out of 33 of the animal phyla, and complex eyes evolved in 6 of 33 animal phyla. But animals with complex eyes make up 96% of species. So this, vision is obviously a really big deal in the animal world. We also talked a little bit about human eyes and sort of the process where they absorb light and refract it to focus it, and then absorb it via the rods and cones in your eye and process some of that information. We talked a little bit about the brain and kind of the complex processing that it does in terms of performing visual recognition and vision. We talked about these 2 systems that we have, the ventral and dorsal system, where the ventral system takes care of a lot of fine-grained recognition, and the dorsal system takes care of some more motion-related tasks, things like planning, reaching out and grasping, stuff like that. And also just about how sort of integral the brain is to computer vision, how some of the information that we get is from our sensors, from our eyes, but then a lot of it is kind of interpolated and processed using our brain, and how important your brain is in terms of processing these images. So hold on, let me get my little screen back up here so I know what's about to happen. We talked, one of the things we talked about were how humans process light, and how a lot of humans have basically these 3 different cones that absorb different amounts of light, and how we interpret the light that we absorb using these cones as color, and how we have different cones that absorb sort of different portions of the spectrum to make up what we interpret as being color. And then we talked about this experiment that people did to actually sort of better understand what color is, these color matching experiments where participants tried to match a single wavelength of light using a mixture of primaries. And these researchers discovered that most people had this sort of similar mix of different primaries, which is great. This means that using computers, we can kind of emulate, using just 3 different colors, a lot of the spectrum that humans kind of see. So we can make this map of color based off of these experiments, and then pick some primaries in this map, and then any color sort of that falls within the bounds of the primaries we pick, we can represent using just those primaries. And this is really cool for obviously doing a lot of computer vision and also doing a lot of image capture. We just need to sort of capture, and we just need to be able to represent these three primaries to be able to represent a really wide range of different colors that humans can see. This also means that a lot of colors that you would like to maybe be able to represent, we actually can't, given just a limited number of primaries. So especially a lot of the spectral colors, the colors that are individual wavelengths, are basically impossible to represent using just primary colors. You actually have to, get a, for example, for 520, for a wavelength that is 520 nanometers, you actually have to get that wavelength to be able to see it. You can't represent it as a combination of other wavelengths. So we talked a little bit about SRGB, which was this standard in 1996 by Microsoft, I think, and how it's sort of the most widely used color space. And we can see on the right side basically a few LEDs that are sort of the common RGB LEDs that people use, and also the cones on top. So these LEDs are basically these LEDs represent the primaries that we picked for sRGB. These LEDs were picked to maximally excite a single cone and hopefully not basically have too much overlap with other cones. And because of this, we can basically change how much we are activating each different kind of cone and then trigger different responses depending on what color we want to represent. So cool. Now we're going to talk about images. We talked a lot about basically vision and color. Now we're going to start transferring some of that knowledge over to computers and kind of figuring out what this all means. Do we have any questions about sort of what we did last week before we keep going? Yeah? No? All right. So it's week 2 of a computer vision class. You guys might be asking yourself, what is an image anyway? If you're not, I'm going to tell you anyway. So eyes have this concept of basically projecting the world onto the retina. And this is a really important concept that we talked about last time in terms of visual acuity, where basically an eye wants to know exactly what direction light is coming from when it passes through the retina and, through the cornea and hits the retina on the back of the eye. So the eyes form this basically projection of the 3D world into this 2D space on the retina, and then your rods and cones will absorb that light and sort of interpret it into some kind of visual pattern. We have a model of this process that's sort of simpler to understand. That's a pinhole camera, and this is something that people have maybe made as a child. It actually works really well, and it illustrates a lot of the concepts that we want to kind of be talking about. So with a pinhole camera, we're basically projecting from the real world through a single point to this image plane at the back of the camera. And there's this focal length involved, which is the distance from the aperture to the image plane. And we can actually sort of flip this around to get kind of an easier to understand representation. So instead of thinking about the pinhole camera as taking the image and going through this aperture and flipping the image onto the image plane, we can actually think about if we go the other direction from the aperture by the same distance, we get basically the same image but flipped. And this is sort of the virtual image. And when you sort of take a picture with a camera, the camera doesn't give you back this like weird flipped image. It does this processing for you where it just sort of flips the image. So what we're going to be thinking about is basically an image. We're going to be thinking about basically these virtual images. We're not going to be thinking about sort of the flipped version of this. So in the simplest form, an image is just this projection. It's a projection of the 3D world onto a 2D plane. And in particular, basically, when you're thinking about an image, and again, in this case, we're thinking about sort of this virtual image, we're going to project light beams from the three-dimensional world through this plane to a single point. So we have this green light beam that sort of, these are not the actual colors, these are just to sort of distinguish the different lights from each other. So we have this light that maybe reflects off of the nose of the plane and goes through the image plane to this origin that we've defined. We have light that travels from the tail. We have light that travels from the wingtip, and light that maybe travels from the wheel. And so we have all of this incident light to this single point, and all we want to do is basically record what that light is, and this is going to be how we're forming these images. So in some sense, an image is just projecting the 3D world onto a 2D plane in terms of how much light is coming in at every point in this 2D plane. Any questions on any of this stuff? So how are we actually going to record this light in practice? This is basically what cameras do. And again, we're going to talk about this in sort of the pinhole model because things get complex when we start adding lenses and stuff. But we will talk about that at some point. So basically, we're going to use this grid of sensors in our camera to record this incident light. And one of the things that we want to record is color information. And this is sort of a point where we run into a little bit of a problem because basically we have this grid of light sensors, and we're pretty good at making sensors that can absorb just any kind of light that comes in and record how much light comes in. But what we really want is color information, and in particular we have these sort of 3 primary colors that we think we probably want to record some information about so that we can sort of display the image to humans again and have them kind of be able to understand what's going on. So how do we map these 3 colors that we want to this image sensor? And what we end up doing is using this filter, which is called a Bayer pattern. And basically what you do is you put a little piece of filter material over the sensor, and it only lets through one kind of light. And in particular, we care about these 3 general colors of light that we talked about, red, green, and blue, because if we use those colors, we can represent the image to humans, and they'll sort of understand what's happening. And we have a little bit of a problem in that we have 3 different colors of light, but we have sort of this rectangular grid that we're going to be recording information on. So what we end up doing is just having basically twice as many green filters as we have of anything else. And this actually makes sense because green is sort of the color that humans have the most visual response to. So we have more, and this is true for basically most cameras on the market. You have twice as many green sensors as you do red and blue, and you get a lot of information just about general lightness from all of the green sensors. You get, obviously color information from red and blue, and then in the end, you're going to basically take all of this data and interpolate it. So instead of having this weird pattern, you have one image that has values at every point. And so all that these little filters are doing is filtering out the incoming light because the sensor underneath is basically going to record any light that hits it. So this kind of makes sense for how we are going to end up recording this image once it gets into our camera. So we talked about how basically images are just 3D projections onto a 2D plane, and we're going to record basically the incident light. So an image is really just sort of this matrix of light where we have this grid, and we want to fill in these values with how much light is hitting the sensor at any given point. Now, we have some sort of restrictions that we want to put on what this image can be. Obviously, we want some sort of sense of more light and less light. So we're going to have higher values in this matrix be more light, lower values be less light. It's going to be bounded in some sense. So no light, obviously, should be representable by something. So it's just going to be 0. There's going to be some point where we hit some sort of maximum, either like the sensor can't absorb any more light, or at some sort of device limit. Your eyes obviously will max out at some certain threshold. There's an amount of light that you can shine in where basically you can't tell the difference anymore. So we need some max value as well. There are a few different options for what we use for this range that we want to be able to span. A lot of times, in terms of storing images, we want to basically make them be pretty small. So we use bytes. and obviously an unsigned byte goes from 0 to 255. And this actually works pretty well. People think that in general humans can see somewhere on the order of like 1 million colors. And if we take, let's see, 255 times 255 times 255, it's 16 million. So that's pretty good. We can represent, probably in practice a lot more colors than humans can kind of distinguish between. And also, we talked about before, there are a lot of colors that we're missing out on anyway, so we actually only maybe need to represent like 3/4 of the spectrum or something. And so these individual values in this matrix, let me just get my mouse back. These individual values in the matrix are going to be called pixels. So we're going to need to be able to have a way of addressing each of these individual pixels, basically. We want some way of talking about them, and they're obviously arranged in this two-dimensional plane, so there are a couple different options. One way is sort of thinking them in terms of Cartesian coordinates. So this is sort of the normal 2D space that you guys are probably used to like plotting out functions on and stuff. It's a little bit weird because for some reason, someone decided that image coordinates should start at the top left-hand corner. So this is basically flipping the y-axis from what people are generally used to in terms of how you would normally use Cartesian coordinates. So in this case, you would address something in terms of its xy coordinate. And what that would mean is that if something is at 0.36, it would be at column 3 and row 6. The other option is using sort of a matrix notation where we're talking about the rows and columns. And obviously, we're just talking about two numbers here, so there's really just two options. In practice, people actually use both of them. So it can get really confusing. You just have to basically be consistent and figure out what you want to use beforehand and make sure you stick with that. So in your homework, we'll be using basically this Cartesian coordinate system where we talk about the xy coordinate, and what the xy coordinate means is just what column it is and then what row it is. You can think of columns as being the x-axis and rows being the y-axis. But again, remember, we're flipping the y-axis so that positive values are down for some reason. Yeah, so again, everyone just does this in different ways for some reason, and we're going to do it the way that all of the vision, or sort of most vision people do, which is have the origin in the upper left. In practice, when we actually start doing transformations and stuff to this matrix, generally what you do is translate it to the origin so that the center of the image is at the origin, and then do your sort of rotations or any kind of transformations that you want, and then move it back. So you just gotta have to kind of figure out beforehand what your coordinates are so that you can end up doing that transformation right. But yeah, we're gonna stick with this for now. So what we really want is a color image, which actually isn't a 2D matrix, but it's this 3D tensor. And for those of you not familiar with the word tensor, it just means a matrix in higher dimensions. So now instead of rows and columns, we're going to have an extra coordinate. It's going to be rows and columns and channels. And each of these individual channels is going to record our color information. So remember, we had the sensor that was recording different red, green, and blue values for light coming into it. We're going to store these in basically separate images, and then we can kind of merge them together after the fact to form our color image. So what this image is representing is basically the first channel is, for this image, how much red light should I have at this pixel? For this image, how much green light should I have at some individual pixel? And then for this image, how much blue light should I have at this individual pixel? And then we can take these images and combine them together. And when we have those specific values of light combining together at that pixel, we get the actual color that we captured, or not the actual color that we captured, but a representation of the color that we captured at each pixel. So again, we can use this process where we can mimic colors to get a fairly accurate representation in terms of what the 3D world was like projected onto this 2D plane. Questions about anything? So again, we have a new problem. How are we going to address these pixels now that we've added on basically this extra dimension? And now we're just going to extend our coordinate system with one value. So we're going to use x, y, and channel coordinates. So again, we have, if we're looking for pixel 1, 2, 0, it's going to be at column 1, row 2, channel 0. And this is what we're doing for homework. Different people, again, will use different things. So if at some point you're interacting with some other computer vision library and you're like really confused because you're trying to get to some pixel and it's not working, you're getting like a different result than you would think about. It may be that they're doing some different sort of system for addressing their pixels. We're going to use the same sort of format when we talk about image sizes. We're going to use basically width, height, and number of channels. So 1920 by 1080 by 3 means that it's sort of a standard HD image. It's 1920 pixels wide, 1080 tall, and it's a 3-channel image. Generally, when you see that an image is 3 channels, it's probably RGB, but you never really know. So a lot of times this stuff is encoded in the file format that you're looking at. Any questions about this kind of stuff, about image coordinates? Yeah. Yeah, OK, so there are a bunch of different ways of storing this. So yeah, again, like sometimes people will use like bytes. They'll use 0 to 255. Sometimes they'll use floating point values, which is often what I use and what you guys will be using in your homework, where we'll just use 0 as sort of the minimum and 1 as the maximum. And people come up with all sorts of crazy encoding schemes for how you can basically shove these values into some smaller amount of space. Usually for doing things like storing them on disk, once you actually like get them into a program and want to start processing them, you don't want them in some kind of weird format just because you want to be able to access the values quickly. Any other random questions? Cool, so we have this 3-dimensional tensor, but when we're actually interacting with it, it's going to be stored in memory somehow. And in general, we usually store images basically as a vector. So we need to figure out some way of transferring this information from this 3-dimensional tensor to this like one linear layout. And there are, again, going to be a bunch of different ways of doing this. So if we just think about a 2-dimensional image, the basic access patterns are row major versus column major ordering. And what this means is basically just accessing the pixels either along the row first or along columns first. Everyone has seen probably this kind of stuff before. Most people, in general, for image processing, use row major ordering. MATLAB, for some reason, always uses like column major stuff for everything. I don't know why. MATLAB is weird. So in general, we sort of refer to these access patterns as being like either height and width or width and height. And this is just going from sort of the rightmost column is what is closest together, and the leftmost is sort of what's farther apart. So if you want to jump between different pixels in terms of width, you don't have to move very far in HW. And if you want to jump between different pixels in terms of height, for HW, you have to jump farther in this matrix that we're going to be laying them out in. So we're going to be using row major for a lot of homework and stuff. This means that basically the first n pixels in your array are going to be the first row. They're going to be different columns in the first row, and then we're going to jump down to the second row and go through that whole row. Then we're going to jump to the third row, et cetera. In 3D, we have more choices. So now we have different channels that we have to think about as well. So the choice that you sort of see on the left is what we would refer to as HWC, where the channels are interleaved. So when we actually bring them over to this array, we're going to have, basically the first pixel that we talk about is going to when we transfer that to our array, we're going to record the red information, the green information, and the blue information. And then we're going to jump to the next pixel. And it's HWC, so we're still actually accessing in this row major fashion. We're just interleaving these channels. CHW, which is the one that we'll probably be using most, you can sort of think about it as taking these different channels and sort of stacking them on top of each other. And then we're just going to do normal row major ordering on them. So you have basically, the first row of the red image, then the second row of the red image, all the way down until you're done with the red image. And then you're going to start it on the green image and record all of that in your array, and then to the blue image and record all of that in your array. So we will be using CHW the most. It's what a lot of libraries use. And here's just a little quiz for you guys to take 2 seconds. So imagine we have this image, and we want to find the entry for this particular pixel. What numerical entry in our array is this pixel going to be ready to go? You'll probably have to use like a calculator. Who's got numbers? Does anyone have numbers? We have a number. 4.5 million? Anyone have a different number? People like that number? That number's right. Come on, mouse. Hold on, I have to get my little clicker to work again. Yes. So again, just a quick review for how we're going to do this. We have some pixel that we want to access that's X, Y, and Z of an image that is W, H, and C in terms of dimension. So the first number that we're looking at in this pixel is going to be what column or just sort of the x-axis. So that is that's the dimension that we're sort of storing first in this array. So we just can add that on to whatever our other numbers are. The next thing that we're looking at is this y-coordinate. And every y-coordinate we go in this array, we're going to have to jump by the width of the image in the array to get to that row. And for every channel, we're basically going to have to jump through this array the size of basically one of these single channels of the image. So in this case, we have this math, and everything's going to be 0 indexed. So we don't have to do any weird like adding 1 or subtracting 1 or stuff like that. So we end up at about 4.5 million. Does that kind of make sense to everyone? Because this will be important for your homework. Some of you probably realize this already. Who has not started the homework? Okay, some people. You guys are lucky, because everyone else has already figured out all of the problems with the homework, and now you're getting all of the answers. What were you saying?
Oh, it's just I didn't see this.
Oh, yeah. So I think we also announced the homework on Mattermost. If people are not on Mattermost, you should be on it, and you can ask us questions, and we will respond to you, hopefully, pretty quickly. So in your homework, this is basically how we're going to be representing images. We have this C struct, which is holding just some very basic metadata, and then it's holding just this big floating point array that contains all of the pixel information. So again, it's really easy to kind of understand our representation of images. It's just the width and height of the image, how many channels the image has, and then just this big array that's storing all of the information. So that's hopefully pretty straightforward, and you guys are playing around with it in your homework, so you'll learn a lot of this stuff just sort of getting your hands dirty with it. So another thing that you guys are going to be doing in your homework that we will sort of talk about a little bit because it's kind of fun in terms of image processing is just transferring back and forth between different color spaces. And in particular, we sort of covered this a little bit last time, but we're going to be talking about this color space of hue, saturation, and value. And we can think about RGB as basically being this cubical color space where every axis is adding or subtracting different amounts of primaries. So you can't see the back corner of this cube, but the back corner of this cube is black because we've taken away all of the blue, red, and green light. And then as you add in different amounts of each primary, you can move around in this cube of different colors. Now, RGB is useful for a lot of different things, but for some tasks that you might want to accomplish, it's not necessarily very clear how you would accomplish them. So for example, if you wanted to, say, shift the hue of your image, so maybe you took a picture of something and everything came out like kind of green or kind of red. And what you really want to do is basically just change the hue of the image a little bit to make it align more with what you think the colors looked like. Or maybe you're trying to rent your house on Craigslist and you want to oversaturate your images like crazy and make the colors like really pop out at you. It's not always clear in RGB how to accomplish a lot of these tasks. So what we're going to do is just play around in this new and sort of different color space called hue, saturation, and value, which is this cylindrical color space that basically encodes this information in a different way. So we're going to have these three axes where one of the axes is the hue, sort of the relative amount of the different colors are in each pixel. One of the axes is saturation, so how much of that color is in that pixel. So hue can be sort of thought of as being independent of how bright or how intense the color is. It's just what general direction is the color. Saturation is sort of the intensity of that color relative to white, which is what we think of as our neutral color. If you mix all of the primaries together, in general, you get a neutral sort of white to gray to black color. And saturation is basically how far away we are from that neutral tone. And value is going to be just the amount of light that we're outputting from that pixel. So the value will basically go from 0, where the pixel is basically entirely turned off, it's black, to being, in this case, we're going to use 1 as sort of our max value, which just means we're outputting as much light from that pixel as we can. And in general, we can sort of think of this geometric transformation that happens when we go from RGB to hue, saturation, and value, or back again, where basically we have this RGB cube, and we're going to take it and sort of flip it on its corner. So the black corner, where we have all of the R, G, and B turned off, is going to be at the bottom of the eventual cylinder that we're creating. And then we're going to sort of squash all of these colors to be on the same plane. And we're going to do this transformation to turn this cube basically into this sort of hexagonal prism or kind of this cylinder. In general, when we're really thinking about it, we're talking about not really the cylindrical version, but more of the hexagonal version. And so when we're talking about hue, the important part here is basically the hue is what direction around this circle you are traveling in or you're pointing in. So hue is kind of independent of what we think about in terms of how much color or how much light is coming out of a pixel, but is more just the direction of the color. And you guys have probably played around with like color wheels before, or sort of this cyclical color space. And that's what we're talking about when we talk about hue. And I think hue is generally sort of the more confusing of the terms. People sort of understand, what saturation is and what value is. But hue can sometimes be a little bit confusing. But also you'll be playing around with this in your homework, so you'll get a little bit more of an intuition for it then. So we still have this three-dimensional tensor that we're talking about, and we still have these three channels in the tensor. We're just going to be encoding different information. So in particular, we have these three things, which are hue, saturation, and value. For the hue in this image, I've just taken our hue information and made it all be the same saturation and all be the same value. So now you can see that what hue is encoding is basically like the bike is red, the wall is yellow, sort of the trees are green. We have this blue kind of floor that's happening, which, again, what we record in some of the other channels of this image help to interpret this information. So when we actually look at the original image, the floor of this image doesn't actually look blue. That's because the saturation is really low for that part of the image. So when you look at the middle image, which is saturation, how intense these different colors are, we see that the ground basically has a really low saturation. Also, the roadway has a really low saturation. So even though in terms of hue, the road is sort of this bluish kind of color, and maybe there's some sort of red or pink kind of colors in there too. All of that information all of the saturation on those colors gets turned way down. By contrast, the bike is this really saturated red color, this really sort of brilliant red color. And the green in the trees is also sort of similarly bright compared to the neutral tone. So we know that those pixels are, much more green than they are kind of neutral or white or gray tones. The value of the image is just kind of this general brightness factor. So a lot of times it ends up sort of looking like a grayscale image. It shouldn't be confused for actually being a good representation of grayscale. That's because basically we're going to, in this transformation, consider red, green, and blue as all being equally contributing to value, which in practice we know isn't true for human eyes. In practice, we know that green matters a lot more for perceived lightness in an image than red and blue do. So it looks sort of like a little bit like a grayscale value, or like a grayscale image. There are other color spaces that do similar things to hue, saturation, and value that use a more perceptually accurate version of value. They use like lightness or luma or some other different kind of metrics for this. And they actually work a little bit better in terms of translating back and forth. This one's just very easy to implement, and it's fun just by itself to kind of play around with. So we're going to be sticking to it for your homework. And there is an extra credit section where if you want to play around with some of these more complex color spaces, you can. So now that we've transferred over to this different color space, there's a bunch of like random little things that we can do with our images that are kind of fun. For one thing, we can basically change the saturation to get more intense colors. And this is something that we've talked about before for people on Craigslist renting out their home. If we multiply the saturation basically by 2, this will still keep the saturation pretty low in a lot of areas where it already is low. And then it will increase the saturation in the colors that are already pretty bright. So we just see that basically the wall and the bike and sort of the green of the trees pop out of this a little bit more. And this is something that if you were just looking at RGB values in the image, it's not exactly clear how you would do this transformation. It would require a little bit more thought process of like, okay, I want to maintain sort of the general color, but I just want to make it a little bit more intense. It's hard to know exactly how you would slide around like little RGB sliders, but once you transfer it into this different color space, into hue, saturation, and value, you can just say, okay, let's just like pump the saturation way up and leave the other 2 channels the same. And we get back this image where the perceptual difference that we want just kind of happens automatically. We can do similar things where if we want to change like the exposure of the image, we can change this value. We can, again, we'll multiply the value image by 2. And this still keeps sort of the dark area of the image dark. It tends to kind of wash out some of the things that are already pretty bright. But this is just kind of an example of random little things that you can do. You can shift the hue around a little bit. So remember that hue is kind of this circle where it's basically the top plane of the hexagon that we're transferring our space to, and or sort of like a color wheel. We can shift all of the colors in some angle around this color wheel and get out an image that has a little bit shifted colors. This is something that I use a lot for data augmentation. So once we start getting into the machine learning techniques that we're going to be talking about later in the quarter, basically a lot of them are really limited in terms of the amount of data that we have. And one of the things we have to do is a lot of data augmentation. So when we start training these like big neural networks, we want a lot of images that we can feed into the neural network to train on. And in general, it's pretty hard to produce labels for these images. You have to have a human go through and label a lot of them. So if you can take the same image and just shift it around a little bit, the network usually can learn some new information from this slightly shifted image without having to go out and actually label additional images. So when we start talking about neural networks and machine learning, a lot of these techniques will come up again as ways to do this data augmentation and basically generate images that have the same content and to humans sort of look very similar, but to computers may look very different in terms of just processing the individual pixel values, and that can be important for reducing some overfitting in some of these systems. Again, you can just do some kind of fun stuff, so you can just change the hue across the board, right? And maybe leave saturation and value the same, and now we've just replaced all of the colors with some individual color, or we can replace it with some kind of interesting pattern. And so you can do some fun stuff with images that way. This is one that I sort of like, where you basically can increase the saturation and then also threshold it. So what we're going to do is cut off the saturation, and anything that's not above a single value, we're just going to set the saturation to 0. So we have this image where there are a lot of really bright colors, and then the rest of it is just kind of grayscale, which is just, I don't know, kind of fun to play with. So this is the kind of stuff that you'll be implemented in your homework. It is not what we think of in terms of like the really hardcore, computer vision. Like we want to understand what's going on in images. We want to be able to make predictions about them. I would argue, though, that like the kind of color space transforms and this kind of stuff is super useful just in terms of like understanding what an image is and what kind of operations you can do on it. It's also that like it's something that will make you, billions of dollars if you make some app where you can share, images with your friend or something. So it's kind of practical and useful. But also a lot of these techniques are things that we use all the time in image processing, just for doing random data processing pipeline stuff. So now we're going to talk about what other kinds of operations we can do with these images. And in general, we're going to start talking about some of the transformations that we can do with images. So interpolation and resizing. So the image is this matrix of values that we talked about before, sort of recording light. And one way to think about it is an image is sort of this function where we're going to map from indices in this tensor, in this three-dimensional tensor, to pixel values. So in particular, an image is going to tell you if you give it 3 pixel values, sort of the row, or 3 pixel indices, the row, column, and channel. The image is going to tell you what the light is at that particular location. So one thing we might want to do is pass in things that are not integers. We might want to pass in real numbers, and in particular, we might want to pass them in for the row and column. Now, in general, channels in images are sort of dealt with a little bit differently than row and columns are. So when you think about like the rows and columns of an image, they sort of represent this this two-dimensional projection of the world where we have two-dimensional space where you can sort of move smoothly between these different pixels. Whereas when you think about different channels in an image, you can't really interpolate between the different channels because they mean different things. So it makes sense to kind of access or want to know, for example, how much light was at pixel 1.5, 2.3 or something, because that's actually a point in this two-dimensional space that we're talking about in sort of our image. It doesn't make a lot of sense to say, how much light was there at channel 1.5, because sort of the difference between channels are a discrete entity, whereas the rows and columns are sort of this open space that we're talking about. So in general, we're going to pass in potentially non-integers into this image function and get back some kind of value. And we're going to do this using some form of interpolation. So first, we're just going to talk a little bit about our coordinate system in images, because we've been talking about sort of these rows and columns. But what an image really is a bunch of discrete points where we've recorded this information about the light. So really, these still have sort of some diameter. These sort of circles have some diameter to them. But imagine that they're just actually individual points in two-dimensional space. And what this represents is that we know the light values, or sort of the incident light at each of these individual points, but we don't necessarily actually know anything about sort of the space in between these different points. And in general, when we talk about sort of these pixel values, we're starting again at 0, 0. So if you look here, we sort of, you may sort of think that kind of the leftmost corner of the image is, or sort of the top left corner of the image. I wish I had a little pointer. You may think that sort of this is the top leftmost corner of the image. But in practice, we don't actually have any recorded information for sort of anything going on up here. The first piece of information that we have, or the first pixel that we have sort of information for, the first location, is actually just this discrete point. And then when we display these images, these LEDs sort of spread out and have some kind of leaking into the space around them. So it fills in, some of this information with just whatever this pixel value is. But actually the sort of point in space that we should be concerned with, where we have recorded information, is just at these individual points in sort of this gridded layout. So again, we have this kind of weird dichotomy in terms of the way we think about images as being these pixels that have some size, when actually what we've recorded is just at individual, basically, points, we have specific information for those points. And in particular, if you wanted to, say, double the resolution of an image, you would be trying to create this new image that has twice as many pixels. So the red overlay here is just an image that we might want that would have twice as many pixels as our old image. But the new values that we would want for this image fall in sort of a weird space. So they don't basically start at 0, 0. They start basically offset a little bit from our original image. So kind of this first pixel that we might want to have information for is a little bit in kind of the negative area of this image. And that's fine. We'll have ways of dealing with all of this stuff. This is just something that you should keep in mind for future homeworks when we start doing some of this image resizing stuff. Just keeping in mind, basically, the difference between the coordinate system and how we kind of generally think of images. And there are just a few pitfalls kind of associated with this kind of coordinate system transformation stuff. So there are a couple different methods that we're going to use for image interpolation. And they have different kind of trade-offs, different positives and negatives. So nearest neighbor is kind of the easiest, sort of most straightforward approach to doing image interpolation. And basically when we're passed in, so again, remember that we're going to be creating this new function where we can pass in real values instead of integers. And we want to get back some kind of pixel information for that value. And with nearest neighbor, all we're going to do is just look at the closest point in space where we have some information. And then we're going to return whatever that pixel value is. So for example, if we're passed in x and y, we're going to round x and y to the nearest integer value because we're assuming that we basically have our information laid out in this grid. And we're going to return the image value at those x and y coordinates, and we're going to keep z the same because, again, it doesn't really make a lot of sense to kind of interpolate between different channels of an image. Now, there are some downsides to nearest neighbor. We end up with getting sort of this blocky image that you can see on the right-hand side here. So this is trying to upsample this very small image by a factor of 8. And in general, it's actually pretty hard to do this and get anything that looks kind of sensible. So oftentimes when we're using these interpolation methods, what we're really doing is just making small changes to an image. And that's when they sort of work best, is if you want to shrink an image by 30%, or if you want to increase the size of an image by 20%. These interpolation methods, all of them will work to some degree. And when we start doing these really big transformations, we probably want to use some other different techniques. But just to sort of really get a grasp on what these different techniques are doing, we'll be using just this one example of if we want to make this one image a lot bigger. So this is what nearest neighbor looks like, where basically we're just going to find the closest pixel. There are some weird pitfalls that you can run into. In particular, if you just try to do the naive thing of doing some kind of integer division in C, you're always going to be rounding towards 0. This shouldn't also say round down. It should say round towards 0 because when you're in the negative domain, it will basically round up. But if we want to do some kind of interpolation, oftentimes we have to remember just to actually be using these rounding operations. So if we have some kind of data that has a little bit less structure to it, sometimes maybe nearest neighbor is one potential option, but we might want to use some sort of more complex interpolation scheme that gets us a little bit better results. So for less structured data that isn't on this regular grid, we can use a thing called triangle interpolation, which is actually really cool and widely applicable to a lot of domains where we're not recording on this grid, where we maybe just have a few sort of sporadic recordings across some two-dimensional layout. So in particular, if we want to know what interpolated value this black pixel should have, we're going to look for some kind of close bounding triangle. And then we're going to interpolate based on the pixel values of this bounding triangle, of sort of the corners of this triangle. So what we're going to do is basically attach each of the points in this bounding triangle to the triangle that we care about. And we get 3 more triangles, right? So what we want for this pixel is, it looks like it's pretty close to this red pixel, and it looks like it's kind of far away from the green and blue pixels. But still, it should have some information from those pixels as well. So we want some notion that maybe the pixel on the left should kind of contribute the most because that's where it's closest to, and maybe the green and blue pixel should contribute a little bit of information, but it should be less information than this red pixel because it's not as close. So all we're going to do with triangle interpolation is calculate the areas of each of these different triangles that we've formed. And then we're going to weight the values for how much the pixel that we have in question, Q, gets from each of the 3 pixels around it based on the area of these triangles. And this kind of makes sense. So if Q were actually just sitting on top of V3, the entire triangle would be red. Everything would be sort of A3. And in that case, all of that pixel's information would just come from the red pixel. If the pixel were, if these were sort of an equilateral triangle and the pixel were right in the middle, all of the triangles would be the same size, and it would be getting information equally from each of the different nearby pixels. One important thing just to note with this is that we really want to normalize this equation based on the total area of the triangle because we don't want our interpolation method to basically be scaling up or down these pixel values, we want them to all sort of be the same. So we want the coefficients that we're multiplying by to sum to 1. And an easy way to do that is just to divide this whole thing by the sum of all of these coefficients. Yeah? Yeah. I am not totally sure. That's a good question. So I can look into that and get back to you a little bit on it if you want. I think area calculations in this case are pretty easy to do. Maybe it's just that distance calculations take a little bit more time, are like a little bit more complex, and then you have to do a little bit more complex normalization, basically. Any other questions about triangle interpolation? So again, this is often not something that we'll be using for things that we typically think of as images, where there's this like really regular grid structure. But for a lot of imaging domains, you have a sensor that is sort of recording just any kind of event that happens. And you might get all of these different values that don't necessarily have any kind of regularity or pattern to them. But it still might have some of these kind of typical properties that you would think of as an image having, and you might want to do some interpolation on it. So just at some point in the future, if that happens, you'll think back on this class and you'll say, oh, I can use triangle interpolation. That's a good way of doing this process. So another technique is bilinear interpolation. And this is, a technique that you're going to use for sort of this regular gridded layout, so something that we normally think of as being an image layout. And in general, it's a pretty good mix of something that functions really quickly, that has really good runtime, but also gets pretty good results. So it's actually very similar to triangle interpolation. That's why it's nice to kind of cover triangle interpolation first. So we're going to find the closest pixels to this point that we're kind of interested in. And then we're going to start drawing some boxes around this point, basically. So we're going to connect all of these pixels together. And we're also going to connect these lines to the pixel in question. And you guys maybe know what's coming. We are going to fill in the areas of each of these different boxes. And then we're going to calculate the coefficients for how much each pixel should contribute to this interpolated value based on the area of each of these boxes. So again, we have this same kind of plan where the amount that pixel V1 will contribute to this interpolated value is weighted by the area of box A1. The amount that A3 is going to contribute is weighted by the amount that the amount that V3 is going to contribute is weighted by A3, et cetera. And we still need to normalize these areas. Now for images, we're generally in a pretty good situation because we think about pixels as being basically one distance apart. So the sum of all of these areas is already going to be 1. Basically, the area of one of these large pixel boxes is 1. So we don't actually have to divide by 1. That doesn't do anything. So that's kind of nice. But in general, if you're in some different coordinate system where pixels aren't 1 unit apart, you may need to normalize this equation to get the right value for your interpolated pixel. Does that kind of make sense to people? So the reason that this is called bilinear interpolation is because it can be thought of as basically a linear interpolation between two different linear interpolations. So in general, if we're trying to interpolate the value of q, we can think about q1 and q2, which both lie along some axis. And q1 is going to be a linear interpolation of v1 and v2. And q2 is going to be a linear interpolation of v3 and v4. And then q is going to be the linear interpolation between q1 and q2. And if we think about how we would basically linearly interpolate between v1 and v2, we're just going to use, this time we're actually going to use the distance, so d1 and d2. And the same thing for interpolating between q2 or interpolating Q2 between V3 and V4. We're going to use these distances D1 and D2. And then to find this value of Q, we use these values D3 and D4, which are sort of the relative distance in the y direction. So Q is a product of Q1 times D4 and summed with Q2 times D3. And what we really want, or what we really hope, is basically that these two formulations are equivalent. And in fact, they are, and it's pretty sort of simple algebra to show that they are. We can take our formula for, what happened? Sorry, my little screen just went away. So we can take our formula for Q, which is the linear interpolation between Q1 and Q2. We can substitute in the formulas that we know for how we calculated Q1 and Q2, which are just this linear interpolation between V1 and V2. We can do some distribution over addition of this multiplication. And then we can see that basically we have these formulas for the areas of these specific rectangles. So if we just look at V1, we're multiplying V1 by D2 and D4. And when we look at the area for rectangle A1, it's just D4 and D2. So that's great. We can substitute in the areas of these rectangles, and we get back to our original equation. So you can sort of think about it in either of these two ways, basically. Bilinear interpolation is either looking at the areas of these different rectangles and using that as your coefficients, or it's doing a linear interpolation between these two linear interpolations. Yay, that's exciting. So bilinear interpolation works pretty well. So again, we're using it here for scaling this image up by just like a whole lot. It is more complex than nearest neighbor. So in particular, for nearest neighbor, all we needed was just to look up one pixel value, sort of the closest pixel value. For bilinear interpolation, we're going to need these 4 lookups. So we have to look up each of sort of the pixels in this grid around the pixel that we care about. Bilinear interpolation is what a lot of systems will use for just really quick interpolation methods. So for example, if you're looking at some image on your phone and you just like are moving it around or like zooming in and out really quickly, it's pretty easy to do the bilinear interpolation for that pixel or for that image. And generally the results look pretty good. So we can see that now this image is a lot smoother than the image that we got using nearest neighbor. So that's good, and it's not super complex. We're not doing any crazy math. All we're doing is multiplying stuff together and calculating the areas of these rectangles. So that's nice. Bicubic interpolation is just a little bit of a generalization of bilinear interpolation, where instead of doing this linear interpolation of 2 linear interpolations, we're going to be making a cubic spline out of 4 cubic splines of points. Bicubic sampling is a lot more complex, I would kind of argue, just in terms of like looking through the math for how this all works. Calculating these cubic splines generally involves solving this system of equations to fit this third order polynomial to basically 4 pixels along individual axes. And you're going to be doing this a few times. And then you have to do, again, this cubic interpolation over the results. So this is kind of a nice figure just to kind of understand the differences between bilinear and bicubic. So for bilinear, all we needed were sort of the 4 nearest neighbors of this pixel. For bicubic, we're going to be doing a lot more information in terms of sort of the local area of the pixel and what's going on. And in general, basically, we're doing the same process where we're doing an interpolation along one axis, and then we're going to do an interpolation along the other axis. So first, basically, it looks like along the x-axis, we are doing sort of 4 interpolations of where the point falls along this x-axis at different y-axis values. And what that interpolation is again, just fitting this third order polynomial. And then for the specific x value that we care about, at each of these y values, we're going to plug in the coordinate and come up with some interpolated value. And then we're going to fit another third order polynomial. We're going to fit another cubic spline to those values to get our final result. So bilinear interpolation involved doing basically 3 linear fits, and bicubic interpolation involves doing 5 cubic splines fitting it to our data. So bicubic sampling takes a little bit more into account of kind of the local neighborhood and sort of the smoothness over an image. And in general, bicubic sampling looks, sort of similar to bilinear, but there are definitely some differences. I don't know if we can kind of, I have to be able to see what you guys can see. So in general, if you look at the image on the left, we have bicubic interpolation, and the image on the right is bilinear interpolation. And one of the biggest things that you can notice about bilinear interpolation is sort of these lines that you get, or sort of this star formation that you get at individual pixels. Whereas you don't get that as much in bicubic interpolation. You get a little bit more of a smoother kind of result, or a smoother image. So in particular for bilinear interpolation, you can see sort of this star-shaped pattern that we get here. And we don't get a similar result in bicubic interpolation. We get just a little bit more of a smoother image, which is nice and often what we want. So bicubic interpolation involves just a little bit more math and is more complex. But it can get better results, especially on some of these really large image changes that we're going to be doing. So for the homework, you guys will be implementing bilinear interpolation. It's pretty straightforward. I have never implemented bicubic interpolation. It seems complicated, so I won't make you guys do it. So in general, if we want to do some kind of resizing or transformation of our image, we have a pretty straightforward algorithm now. All we're going to do is try to find each pixel in our new image, and we're going to map it to the coordinate system in our old image. We're going to find the interpolated value for that coordinate, and that's going to be the value that we set in our new image. Now, this makes a lot of sense when we're just doing sort of some of these smaller transformations, especially, I think, so for bilinear interpolation, for example, they say it's often not good to basically resize your image more than 2 times or shrink it down by more than 50%. And this is actually really important to keep in mind. So if we want to shrink an image, so for example, this is taking an image and shrinking it by a factor of 8. Both nearest neighbor and bilinear are going to have some weird results that basically happen. And the reason for this is when we start talking about shrinking images, what we really want is to look at some neighborhood of pixels and figure out what that should be represented as when we shrink that neighborhood down to a single pixel. But what happens when we use nearest neighbor or bilinear for doing this shrinking operation is that we actually end up just looking at this very small local neighborhood. Nearest neighbor obviously just looks at 1 pixel, but even bilinear only looks at the 4 nearest pixels, this sort of very small distance from the pixel that we care about. And if we shrink down this pixel by a factor of 8, we're really not looking at enough sort of local information to get a good representation of what this image is. And in particular, we get sort of these staircase patterns that happen where we have some smooth line, and we would like to sort of see in the shrunk down version some representation of this smooth line that doesn't kind of look jagged. But what we end up getting with just kind of these basic interpolation methods are these jagged lines and things like that. So what we're going to be talking about next class is ways to fix this using filtering and looking at sort of local sort of small areas of pixels to get information if we want to shrink them down. But also we're going to be using these same methods for getting a bunch of other information about images. And so this sort of forms the basis of the convolution operations that we'll be talking about for a lot of the future class. So Next time, we'll talk about filters and convolutions, and it'll be very exciting. Hopefully now everyone kind of has a good sense of image coordinates and how to process images. Does anyone have any questions about anything before you all run out of here? Nope. If anyone does, come see me. Otherwise, get out of here.